Hello, Accelerated Chemistry students. This is Ms. Crystal Foley, and this is your Chapter 7, Section 2 notes all over ionic bonds and ionic compounds. Let's start off this section with a couple of definitions. So what is an ionic compound? An ionic compound is a compound comprised of cations and anions. Remember, cations are positively charged, anions are negatively charged. Although ionic compounds are comprised of ions, the compound itself is electrically neutral. So it doesn't have an overall charge, even though positive charges and negative charges bind together to make it. So what is an ionic bond then? The ionic bond is the electrostatic force that holds oppositely charged particles together in a compound. It is a bond that forms between a metal and a nonmetal, and the metal is going to transfer their valence electrons to the nonmetal. So there are three steps in the process. First, we need to form the positive ion. Second, we need to form the negative ion, and then they're going to form the ionic bond because they're going to be attracted to each other.
When one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has one valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion.
Okay, so that's the explanation of how your positive and negative ions are formed and why they are stable. So let's look at an example between sodium and fluorine. So sodium is going to become a positive ion and fluorine is going to become a negative ion, because sodium is going to give its electron to fluorine. So sodium is going to have 8 electrons in its outside shell and be a plus charge. Fluorine is going to have 8 electrons in its outside shell and be a minus charge. So the attraction between the positive and negative ions that are being formed is what's going to form the ionic bond. So a chemical formula shows the number of atoms of each element in the smallest representative unit of a substance. So ionic compounds do not exist as discrete units, but as collections of positively charged and negatively charged ions arranged in repeating patterns. So sodium chloride actually looks like the picture in the middle. It's going to be alternating positives and negatives. So the negatives are going to be our chloride. So the green spheres are going to be our chloride spheres. And that should make sense because when chlorine gains an electron, it gets bigger. And then sodium is going to be the smaller spheres because when it loses its electron, it becomes smaller. So the chemical formula of an ionic compound refers to a ratio known as a formula unit. So a formula unit is the lowest whole number ratio of ions in an ionic compound. For sodium chloride, the lowest whole number ratio of ions is 1:1. So that means that there's one Na plus ion to each Cl minus ion. So the formula unit for sodium chloride will then be NaCl. Although the ionic charges are used to derive the correct formula, they are not shown when you write the formula unit for the compound. So let's look at an example. Let's look at sodium fluoride. So the formula unit, remember, is going to be the smallest whole number ratio between your cations, positively charged, anions, negatively charged ions in the ionic compound. So for sodium fluoride, we are going to transfer 1 electron from sodium to fluorine. So we're going to have Na plus and F minus. The charges are equal and that they cancel each other and make a neutral compound. So the formula unit for sodium fluoride would be NaF. So that means that we have 1 Na plus ion and 1 F minus ion in the ionic bond between sodium and fluorine. Let's look at example 2. Let's look at the example of magnesium and bromine. So we have one magnesium is going to give up one of its electrons to one of the bromines, but it still can give up another electron because magnesium is in group 2, so it will have 2 electrons to give. So that means that since each bromine can only take 1, you're going to need 2 of them. So the formula unit for magnesium bromine would be MgBr2 because you have 1 Mg plus 2 ion and 2 Br minus ions in the ionic bond between magnesium and bromine. Let's look at the last example, aluminum and oxygen.
Welcome to that lecture line, and here's a third example of how to put together a Lewis structure for an ionic compound. In this case, we're going to talk about aluminum oxide. And notice the way the molecule is put together. We have 2 aluminum atoms and 3 oxygen atoms. It'll become apparent very quickly why that is so. Well, first of all, aluminum has 3 valence electrons, so the tendency for aluminum is to donate the 3 electrons. Oxygen has 6 valence electrons, so it has the tendency of trying to grab 2 more and make a full set of 8 valence electrons. Now, of course, 3 and 2 is not the same number, so let's take a look here. This atom can donate 3, and this one needs 2, which means if we have 2 aluminum atoms, they can then donate 6. If we have 3 oxygen atoms, they can then receive 6, and so that's why the relationship between 2 aluminum and 3 oxide forms a molecule like that. So if we multiply this times 2, we get 6 valence electron. We'll multiply this times 3, we get 6 valence electron, and then of course the 6 of the aluminum, extra electrons from the aluminum can be donated to the 3 oxygens that then in total need 6 more electrons. So what that looks like is as follows. We have we have 2 aluminum atoms, and notice that this aluminum has 3 valence electrons, this aluminum has 3 valence electrons, and here we have 3 oxygen atoms. Notice that each of the oxygen has 6 valence electrons, which means it has room for 2 more. And here, these are 6 valence electrons and room for 2 more, and 6 valence electrons and room for 2 more. So what's going to happen is that these 2 electrons are going to end up with this oxygen. This electron is going to end up over here. This electron is going to end up over there. And then this electron will end up over here, and this electron will end up over there. So that's how the electrons are going to be swapped, which means we're going to end up with 2 aluminum atoms that do not have any valence electron in its outer shell, and therefore it has valence electrons in its innermost shell. So we end up with 2 aluminum ions, and since each of those aluminum ions have donated 3 electrons, they now will have a 3+ charge. Then we have 3 oxygen atoms, which now have 8 valence electrons, like so, and since they each received 2 extra electrons above and beyond what they came with, they will then be a 2 negative charge. And then when you put those together, you now have a Lewis structure of that particular ionic compound. So we have 2 aluminums that are 3+ and 3 oxygens with the valence electrons indicated like this, which have a charge of 2-, and you now have yourself the Lewis structure of an ionic compound. So that's a typical way of writing ionic compounds in the Lewis structure methodology. So that's how we do that. We saw a few examples. Now we go on to some additional examples of different kinds of compounds.
Okay, so the formula unit for aluminum oxide after the pictures were drawn was Al2O3. Okay. So remember, we had 2 Al plus 3 ions and 3 O2 minus ions in the ionic bond between aluminum and oxygen. So now that we've talked about how we form these ionic compounds and we form the ionic bonds, let's talk about the properties that they have. So most ionic compounds are crystalline solids at room temperature, and the component ions in such crystals are arranged in a repeating 3-dimensional patterns, which are called crystal lattices. And so the beauty of the crystalline solids comes from the orderly arrangement of their component ions. So remember, these are in repeating patterns, and those repeating patterns are made to make these crystal lattices. So each ion is attracted strongly to itself and its neighbor, and repulsions are minimized because we have a large attractive force between these oppositely charged particles. And so that makes the structure very stable. So when we're talking about the structure, we talk about a unit cell. A unit cell is the simplest repeating unit of a crystal lattice. So the coordination number of an ion is the number of oppositely charged ions that surround each other in the crystal. So in NaCl, each ion, the Na and the Cl, have a coordination number of 6. That is because one sodium ion is surrounded by 6 chloride ions, and one chloride ion is surrounded by 6 sodium ions.
Sodium chloride can be built by first constructing a face-centered unit cell of chloride ions. The smaller sodium ions can then fit into the spaces or holes between chloride ions. Notice that each sodium ion in one of the lattice holes is surrounded by 6 chloride ions at the corners of an octahedron. Therefore, the sodium ions are said to fill octahedral holes.
So, if we were to look at some other examples, for example, cesium chloride, each ion has a coordination number of 8 because one cesium ion is going to be surrounded by 8 chloride ions, and one chloride ion is going to be surrounded by 8 cesium ions. For an example like titanium dioxide, it forms tetragonal crystals. I do not know how to pronounce these sometimes. And so the coordination number for the cation of Ti plus 4 is 6, and each Ti ion is surrounded by 6 O2 minus ions. So the coordination number for the anion O2 is 3, and that's because each O2 ion is surrounded by 3 Ti4 plus ions. So if we continue talking about the properties of ionic compounds, they are hard, brittle solids and that are very rigid, and this is due to the strong attractive forces that hold the ions in place, and the force strong enough to break the ions apart will crack or separate the solid where the unit cells are incomplete, usually around the edges of the crystal. Ionic compounds also have high melting points and high boiling points, and this is due to the very strong attraction between the ions that it has. Remember, opposite charges do like each other a lot, and so these things are going to be very hard to separate from each other. They are also soluble in water, which means they can dissolve in water, and they conduct electricity only in molten or aqueous states. And the reason why they conduct electricity is due to their free moving charge. And so we consider these things to be electrolytes. And electrolytes are compounds whose aqueous solution conduct electricity in an electric current. Why does that happen? That happens because when we dissolve anionic compounds in water, we actually can see that the ions are going to dissociate or separate from each other. So when we look at this, the opposite charges of the water are going to be attracted to the oppositely charged ions in the crystal structure. So that will allow for those crystal structures to have ions in solution when dissolved in water. If we were to look at how we can melt salt, we can conduct electricity that way if we make sure that those ions are freely flowing. Remember, if something is a solid, those particles are not moving. Those ions are not freely flowing. But if we heat them up, we're going to increase the spacing between them so that they can flow more. And so we are going to be able to then light a light bulb because those things will be able to conduct electricity. We just need to get it to a really, really, really high heat though, because ionic compounds have an insanely large amount of attraction between them. So that will allow for us to not separate them as easily.
Again, would you be opposed to me stapling those periodic tables instead of paper clipping?
Mm-mm.
Okay. I just thought I'd ask before I did something.
Yeah, that's fine.
Cool.
And as always, this is the end of your Chapter 7, Section 2 video notes all over ionic bonds and ionic compounds. And as always, all of this information has been acquired and adapted from Pearson Chem's 2012 edition of the textbooks, resources CD, and pearsonchem.com. Thank you very much.